Hello everyone, welcome to this 19th lecture in the NPTEL course on Riemannian geometry. So in the previous few lectures we talked about covariant derivatives of vector fields, covariant derivatives of forms, generalized to covariant derivatives of tensors and so on. And in lecture 17 we also introduced this notion of a Levi-Civita connection. So that's a sort of canonical connection that can be associated to any Riemannian manifold. So from now on, for the rest of the course, we only consider the Levi-Civita connection on a Riemannian manifold Mg. Okay, so whenever I talk about connection, I'll always mean the Levi-Civita connection. Okay. All right. So having said that, the purpose of the next few lectures is to finally introduce curvature in a rigorous way and to discuss various properties and various aspects of the curvature tensor. As you will see, the curvature tensor is a very complicated beast. So what we'll do is we'll try to calculate the curvature tensor of a few examples. We'll also look at submanifolds sitting inside hypersurfaces sitting inside Rn and so on, and try to see if we can calculate its curvature. And then we'll also introduce another form of curvature called the sectional curvature, which is slightly easier to imagine, right? Okay, but to begin with, I want to introduce what is called as the curvature endomorphism of Riemann. Okay, so here's the definition. The Riemann curvature endomorphism which will be denoted by R. So it's a map that takes in three vector fields, okay, and spits out another vector field. So symbolically we will write it in the following way. It will take in x, y, z, and the result we will denote it by R of x, y acting on z. So by definition, R of x, y, z is just going to be the covariant derivative of z, first in the direction with respect to y, then with respect to x, minus the covariant derivative of so maybe, sorry, let me write it like this. So it's going to be the commutator of the covariant derivatives with respect to x and y applied to z, minus a correction term that comes from the Lie bracket. Okay. So let me write this out, let me expand this out. So this is simply R of x comma y on z is simply nabla x nabla y z minus nabla y nabla x z minus nabla x bracket xy of z. Okay. So this is the definition of the Riemann curvature endomorphism. So just as a quick example, let's say we are on Rn with the usual flat metric, with the usual metric, then one can easily check, because what is the Levi-Civita connection on Rn with the usual Euclidean metric? Well, that's just the usual component wise differentiation, right? And then for the usual differentiation, we have this theorem that we learn in any multivariable calculus course, namely Clairaut's theorem, right, which tells us that mixed partial derivatives are equal. So that in the present context would imply that the curvature endomorphism vanishes for all choices of x, y, z. Okay, so that's an easy check. For instance, one can take the standard basis vectors, because we are working on Rn. These actually give basis vectors on all of Rn, to the tangent space on all of Rn. So so here so maybe I should let Z be any vector field. Then of course the standard basis vectors commute under the Lie bracket, so this term will disappear. So this will just be this, which is precisely del square Z by del xi del xj minus del square Z by del xj del xi, which by Clairaut's theorem is 0. So for Rn with the usual Euclidean metric, the curvature endomorphism vanishes completely, identically. Okay. All right. So key observation with respect to this this curvature endomorphism is that R is C infinity multilinear, i.e. we basically get these three identities. Okay, so the proof is actually, I mean, you just write down the definition and use the Leibniz rule over and over again. So maybe I'll leave 1 and 2 as exercises and only prove one of these, namely the third one. Okay, so so let's quickly give a proof of this. So what is this? This is this acting on Fz minus this, right? So so this is nabla x, nabla y acting on Fz minus nabla y nabla x acting on Fz minus, I can directly apply the Leibniz rule here, that will be bracket xy acting on f times z minus f times this, right? Okay, so let's evaluate the first two terms again using Leibniz rule. So the first term is basically nabla y of Fz. Nabla y of Fz is simply this plus f times nabla y of z. Similarly for the other term, and then the Lie bracket terms. Okay, but again you apply the Leibniz rule. So this acting on this will be xy of f times z plus y of f times nabla x z plus x of f nabla y z plus f times nabla x nabla y z. Okay, similarly the y terms, so there will be yx of f times z minus x of f nabla y z. So I am just changing the role of x and y, minus y of f nabla x z minus f times nabla y nabla x z, right? And then of course the Lie bracket terms. Okay, so now you can collect terms. So if you look at this term, that's just the Lie bracket applied to f times z, so that will cancel with this term. So all these three terms will cancel. Similarly, you can collect the following terms. If you look at this term, that cancels with this term. Similarly, this term cancels with this term, and in the end you are only left with the following. Right, which is simply f times the curvature. Right, so this proves the third identity. Yeah. Okay, similarly you can prove the first two identities. So that should also tell you why we needed, so the one could have, a naive way to define the curvature would just have been a commutator of nabla x and nabla y, right? But the reason why you need a correction term coming from the Lie bracket is so that you get the C infinity linearity, multilinearity. Okay, C infinity multilinearity is important because of the next remark that I am going to make. Okay, so let me make a few remarks. Firstly, C infinity m multilinearity implies, like we saw with tensors, one can leverage C infinity multilinearity to mean that for all points P in M, one can talk about the value of the curvature endomorphism at the point. Okay, and so then this will be an R multilinear map from 3 copies of the tangent space to the tangent space. So C infinity M multilinearity allows you to localize at a point, right? This was something, this was the tensor principle that I described when we did our quick review of tensors, right? So that's the advantage of having C infinity multilinearity, and because we wanted something like this, we wanted a sort of tensorial quantity, we had to have this correction term involving the Lie bracket. Okay. So in other words, we can talk about the curvature endomorphism at a point. Okay, the second point is that R can actually genuinely be thought of as a tensor. So R can be thought of as a 1-3 tensor. So what is a 1-3 tensor? Well, that takes in a one form and takes in 3 vector fields and spits out a smooth function, right? So it takes in omega 1 x, y, z, and the C infinity function that it spits out is the following. You apply r, x, y, z, that's a vector field, you simply apply omega to it. Okay. So because of C infinity multilinearity, one can check that TR is in fact a 1,3 tensor. Okay. So from now on, I make no distinction between TR and R. So from now on, we make no distinction okay. All right. So so this was the second point. So maybe I want to make another point. So given vectors, let's say uv in the tangent space to M at P, I can think of R uv as a map from TPM to TPN, which is R linear, right? So if you fix U and V, then R of U and V can be thought of as an endomorphism of the tangent space at that point. This is the reason that this R is called the Riemann curvature endomorphism. Okay, because if you fix the first two entries, you can think of it genuinely as an endomorphism of the tangent bundle, of the tangent space at that point. Okay, so now this finishes our remarks, but now locally, because it's a 1,3 tensor, given any local frame, let's say E1 up to En, one can write R of Ei, Ej acting on Ek. So that will be another vector. So you can write that as R I J K L E L. Okay. So these are called the components of the Riemann curvature endomorphism with respect to this local frame. Okay. So as a tensor, one can write this in the following way. So as a tensor, one can write R. So remember, it's supposed to be a 1,3 tensor. So as a 1,3 tensor, one can write this as R I J K L epsilon I tensored with epsilon j tensored with epsilon k, where epsilon is now the dual basis to EIs, tensored EL. Okay. So then if X is this is written locally as Xi EI, Y is written locally as Yj EJ, Z is written locally as Zk Ek, then R of X Y acting on Z is simply given by R Ij K L Xi Yj Zk, okay, times EL. Okay, so that's the local expression of my Riemann curvature endomorphism. So along with this endomorphism, there is another tensor that is often useful. It's equivalent to the Riemann curvature endomorphism, but that thing is called the Riemann curvature tensor. Okay, so the definition, so it's denoted by Rm. So this now takes in sort of 4 copies of vector fields. So these are 4 copies and spits out a smooth function. So Rm of x, y, z, w is simply R of x, y, z inner product with w. Okay. So locally again, one can write Rm as R I J K L, epsilon I tensored with epsilon j tensored with epsilon k tensored with epsilon L, i.e. Rm is a 0,4 tensor, right, where these local components R, I, J, K, L is simply given by lowering an index in the curvature operator. So this is simply G L M R, I, J, K, M. Okay. So you sum over this, that just means you are lowering an index. This is analogous to the flat operator, which when applied to vector fields lowers the index to give you a 1 form, right. It is something similar here. Okay, so maybe I'll end with the following proposition about naturality. Okay. So if phi is a local isometry, then for any x tilde, y tilde, z tilde, which are vector fields on M tilde, if you apply the curvature endomorphism for G tilde, so that will give you another vector field on M tilde, and then apply the derivative map. So push forward via the derivative map, that's the same as R G of the push forwards. Applied to d phi of z. Okay. So consequence of this is the following. One can talk about the following example now. So we go back to these examples of these flat tori that we had introduced a few lectures back. So let me remind you of the setup. So let L be a lattice in Rn. Then the Euclidean metric naturally induces a metric GL on the torus TL, which is simply the quotient of Rn by the translation action of the lattice. But now recall that the natural projection map by definition, since GL, by the way GL is induced from Rn, that means that the natural projection map is a local isometry. Okay, so that means that if you look at the Oh, I should have also mentioned that one can write down the same thing for the curvature tensor. So for the curvature tensor also you can see easily that Rm tilde is simply the pullback of this curvature tensor. Okay. Right. So here Rm of this induced metric on TL is simply the pullback. Sorry, I should. Right. So because Rm of the Euclidean metric is identically 0 and phi is this pi is a local isometry, this automatically implies that for these tori also the curvature vanishes completely. Okay. All right. So the other thing I should have mentioned in the previous slide is that Rm is defined using the curvature endomorphism, but it's equivalent to the curvature endomorphism because conversely each of these components is given by simply raising the index of the curvature tensor, right. So the curvature tensor, the 0,4 tensor and the curvature endomorphism, the 1,3 tensor, they are basically equivalent via just raising and lowering of indices, right. So whenever convenient I will talk either about the curvature tensor or the curvature endomorphism, it does not really matter. Okay, so the point of this is that all these toris basically have 0 curvature, okay. But now notice that each of these toruses, so let us take for instance dimension 2, right. So then this torus is diffeomorphic to a product of 2 circles, right. So this gives us and I mean this diffeomorphism, if you look at the fundamental parallelogram, you basically identify these 2 sides, right, the opposite sides, and so this gives us a nice picture of a donut. Now a donut can be thought of as a surface embedded inside R3. So the Euclidean metric on R3 will induce a Riemannian metric on this donut, right. But obviously this Riemannian metric, so let's consider for instance the restriction of this Euclidean metric to this donut which I will denote by D. But this metric is clearly not 0, right, because for instance if you look at a point on the outside of the donut, as I explained I think in the first maybe the third lecture, that the points on the outside of the donut are look very similar to points on a sphere, so they are positively curved. On the other hand, points in the inside, they basically look like a horse saddle, right, so they are negatively curved. So clearly a donut embedded inside R3 does not have 0 curvature. On the other hand, if you look at the natural metric induced by this translation action, that actually does have 0 curvature. So even though both are diffeomorphically the same manifold, it's just a donut, the Riemannian metrics are different. The Riemannian metric of a donut which is induced from R3 is different from the intrinsic Riemannian metric induced from this lattice structure in R2. Okay, so that's a distinction that one should keep in mind. So that is why these tori I had called flat tori. Okay, so flat basically just means that the curvature is 0. We will talk more about flat manifolds and I think in maybe 2 lectures down the line, okay, or maybe the next lecture perhaps, we will see. Alright, so that's it for this lecture. In the next lecture I'll talk more about properties of the curvature tensor, and that will be the theme for the next few lectures. Alright, so thank you for your attention and I will see you in the next lecture.